For this next problem, let's talk about probability plots, how they're constructed, and what they're good for. What they're good for is to determine whether or not a sample can plausibly be described as following the normal distribution. And unlike the other videos in this series, I'm going to simply talk through the PowerPoint that we did when we discussed this in class. So there's going to be no written computation on this one. I just wanted to kind of describe how the process is done. Obviously, this is a fairly time-consuming exercise, and so this is more of a conceptual question as opposed to a computational question. The thing that we use to the kind of question we'd answer is, here we have 50 salaries of U.S. governors, and the question is it plausible to think that the data is approximately normally distributed? Now, clearly there's no physical law that says that the data will be normally distributed, but the question is it plausible to model it in this way? The way that we do this is by constructing a probability plot, and the punchline is going to be the line here. The way that we do this is we set up x and y coordinates. The y coordinates will just be the values in order, and the x coordinates will be percentiles off of the bell curve. So for example, the smallest salary was $70,000. That corresponds to I equals 1. And so when I equals 1, we compute 1 minus 0.5 divided by 50. And so just doing that calculation, 1 minus 0.5 divided by 50 gives me 0.01. Okay, now notice I did not put 70,000 in for I. I put 1 in for I, corresponding to the smallest, the first value in the series. Next thing that I do is figure out the first percentile off the normal distribution. Using Excel, the command is normsinv. Using a TI calculator, the command is invnorm, and we get the first percentile off the normal distribution. And so here's my x-coordinate, and here is the y-coordinate. We do this again. For the second smallest salary, $77,028. For the second smallest salary, I is equal to 2, so I plug in 2 for I, not 77,000. 2 minus 0.5 divided by 50 works out to be 0.03. And so I figure out the third percentile by doing norminv of 0.03 or else invnorm of 0.03 to get this x-coordinate. And then I repeat this for all of the entries in the list. And of course, I've got 50 governors, and so I do this 50 times. So the number 50 that appears here appears because we had 50 things in the list. So then we plot these 50 xy pairs. So once I have these two columns, I can ignore this blue column here and worry about these two columns. And I plot the x-coordinate versus the y-coordinate, and I get a plot that looks kind of like this. This line, this data approximately follows a straight line. It's not perfect, and I don't expect it to be perfect, but it is approximately following a straight line. And so it's plausible that the data follows a normal distribution approximately. So that is what a probability plot is good for. We see in these pictures, here I have data that comes off a bell curve, and samples of size 100 this time. And none of these plots in blue, the samples, follow the bell curve exactly, especially the very smallest values and the very biggest values, but in the middle, it follows a straight line reasonably well. And so we would say from the data that this does follow a bell curve, which it's supposed to because the data did in fact come off a bell curve. However, if I have something that's a lot narrower, like this distribution here, this I believe is a t-distribution with maybe about 3 or 4 degrees of freedom, then we see, because we have something that's very narrow in the middle, we have this kind of S shape that goes like this, where it's too low to the left and it's too high to the right, and that consistently happens for all these pictures. So that kind of S shape is an indicator that it is not approximately normal. In this case, it is too narrow in the middle and the tails are too wide. Here's another example of something that's S-shaped, but this time the S-shape goes that it's too high for the small values and it's too low for the big values. And so again, we would conclude that this is not normally distributed. Something else that can go wrong is a picture that goes like this. Here I have something that is skewed positively. So I have a tail that goes off to the right, and there's no corresponding tail going off to the left. And we see for these pictures that the picture tends to go like a like a kind of exponential growth like this, and it is not being followed. It's not following a line. It's too high to the left, and it's also too high to the right. The other thing that could go wrong is something that's negatively skewed. It would be too low to the left and then too low to the right. But if we have a picture that looks like this, or a picture that looks like this, then we have something that is approximately normally distributed, and because the data approximately follows a straight line. So I did not do the calculations in this particular video. There's another video on the website that, of course, that we actually did the calculations. This is more of a review as to how we do the probability plot and why it is important.